Hello, and welcome to today's webinar, Vast Energy Savings and Increased Occupant Comfort Using the Belimo Energy Valve, presented by David Riffle and Kevin Leathers. We really appreciate you joining us today. My name is Ron Pilkowitz, and I will be your moderator today. Because we know you will want to watch this webinar again, it will be recorded and posted on Belimo's YouTube site. There will be a question and answer session at the end of this presentation, and we'd like to hear from you. At any time, I invite you to type your questions into the question box and I will read them aloud during the question and answer session. We will answer as many questions as we have time for, or otherwise you will receive an answer via email. If you are having any difficulty, please type me a note in the chat box and I will try to assist you. Please note that this presentation is available as a handout and you are able to download it if you'd like. I would like to now turn this presentation over to Dave. Thank you, Dave.
Thank you, Ron. Good afternoon, everybody. Again, thank you for taking your time today. And first things first, we really wanted to say thank you. This has been a
manager for Belimo in Tennessee. And this story started back when Chad Lovell from JLL attended a Belimo new product lunch and learn at one of our distributors in the Nashville area. And one of the highlights of that presentation was the Belimo Energy Valve. And Chad came up to me afterwards to chat a little bit and specifically mentioned the energy valve, that he was very interested in us coming to see his building because he was experiencing a couple of challenges, mainly low delta T throughout this building that was causing him to pay significant thermal inefficiency surcharges to the Nashville district chilled water plant. The Nashville District Chilled Water Plant that you see pictured here is a massive complex down on the river near downtown Nashville, and it serves around 50 buildings throughout downtown Nashville. And each of their customers has a contracted delta T rate. If those customers do not meet that contracted delta T, they're hit with a monthly thermal inefficiency surcharge. In JLL's case, their contracted rate was for a delta T of 14, but they were returning a delta T that averaged between 4 and 6 degrees. Therefore, they were paying a thermal inefficiency surcharge that reached $12,000 to $13,000 per month during the peak months. There also were some new EPA regulations that really caused a drastic drop to their Energy Star ratings. So in talking with Chad, we really felt that the Belimo Energy Valve might be the perfect solution to address all of these issues.
Thank you, Kevin. So what is the Belimo Energy Valve? So it's a dynamic balancing valve that consists of a couple of different parts. Essentially, it's the same characterized control ball valve that we've been using since 1999 with an actuator on top that's now become a smart actuator. It has a web server, it can do some data logging, it's a smart communications device, and it has a lot of abilities that some of our actuators did not have in the past. We also attached a ultrasonic wet flow meter to it as well. So the two devices now talk. So not only do we look for position, but we can look for flow. This control valve is now a flow meter as well, and it's pressure independent because of this flow meter. After that, we add two platinum-based RTV temperature sensors. So essentially a temp sensor on the supply and a temperature sensor on the return. And we can now look at that heat transfer across our device. And the last thing is there's some logic or smarts. Again, there's some delta T management and some other brains that now live in this smart actuator that allow us to do some pretty interesting things. Overall, we can measure, observe, record, and trend data, basically. So what do we know? What led to all this? We know that coil overflow leads to an inefficient delta T, which in this scenario can and does lead to district chilled water penalties. And here we have a real example we can give, and this is just an example, but referencing some of the numbers from the Nashville buildings we're going to talk about today. On the right side of my screen, I have a typical heat exchanger or a coil we can see, and on the top in blue, I have my entering water coming from my district chilled water plant at 42 degrees, passes through my heat exchanger or coil, takes a nice heat transfer, and leaves the return at 56 degrees in this scenario, or a 14-degree heat transfer. What we know, as we mentioned before, is that systems and coils tend to overflow. So if we can watch my graph up here on the top left, now we'll see that as flow increases, this causes the coil to overflow and become inefficient, which means I lose my heat transfer. I don't have the same rate of time to take that heat transfer out of the air to water exchange. My delta T drops. In our example here, we went from 14 down to 4. When that happened for the state of Tennessee, that increase that happens to their water, or that decrease in delta T, we could call it, is an inefficient use, and that caused that 12 to 13,000 in the worst case month penalty fee they were paying. This graph on the bottom shows that depending on what the delta T is, the rate that they would pay changes. These are just examples of rates. They're not perfectly specific to the state of Tennessee, but gives us a nice example of how when we're not using the chilled water as designed, we get charged a different amount. Now that we know how that system works, we can look quickly at how the actual energy valve works. So this is explaining the smarts, or the logic that we referred to earlier. In this graph, if I kind of start on the bottom, I have the supply coming in the bottom of this example. The bottom pipe shows 42 degrees. It passes through my air handler unit on the right. I take a heat exchange as the air passes over it, and I go out the top on my return through my energy valve with 55-degree water. In this example, 42 in, 55 out, a nice 13-degree heat transfer. I have a couple fun dials above here. My first says CS, which is the control signal coming from the building automation system. The second one right above my valve is the valve position, or the P dial. And the last one to the right by my coil is my actual delta T. So we can see here, everything is at design or close to design. So our system is pretty happy. 42 comes in, 55 comes out on my water temp. I have a nice heat transfer happening. As my system starts to overflow, as our control signal opens up, something different will happen. So if we watch our dials now, we can see as we click, our control signal is increasing, our valve position is opening or increasing, our delta T has dropped. We were before at around 13 degrees, and in this example, we've dropped to 6. These numbers are relative to the case study that we're going to talk about in a second. And we can see we're not getting that good heat exchange out of our system. Essentially, we're not using the water. The water passes through the coil too fast. We can't get that efficient heat transfer out of it. The valve sees this happen and has some logic that says I need to take over. So delta T manager goes active. We can see the control signal is not moving. The valve position is moving, and the delta T has increased. We've gone back from that 6 back up to where we want to be in that 13-ish range. So water is now coming in at 42, again, leaving at 55. This is what we're doing. We're controlling that delta T to make sure we're efficiently using the water in our system. In the example we're referring to, we're eliminating the overflow and not paying just to pump water around our system.
So Dave just gave you a really good idea of how the energy valve operates. And I want to talk to you a little more about this project in Nashville and what we found when we went to visit. So after that lunch and learn, Chad Lovell invited us to visit his facility and take a look. We went to Citizens Plaza in downtown Nashville as part of the State of Tennessee Capitol Office complex. And with Chad, with some representatives from the state of Tennessee, and with Steve Ribka, who was our regional applications consultant at the time, we walked through Citizens Plaza. This was 2013, and we found just a standard Class A office building, 15 stories, that contained on average around 1,000 workers per day. In those mechanical rooms, it was a very typical oversized air handler, oversized globe valve, oversized coils. So looking at the goals that JLL had for this building, which was to lower the chilled water usage and get rid of those thermal inefficiency surcharges, our goal was to optimize his existing coils and his existing air handlers by installing energy valves. And that's just what we did. We After that first meeting, we sat down with the state and with JLL, and we decided to come up with a pilot project to test out the energy valve and prove what we were saying and that they would be successful. So we took 3 energy valves and we installed them on a low floor, a medium floor, and a high floor. So we'd get a good average as far as distance from the pumps. And we saw immediate results. We did regular downloads of data on a scheduled basis, either Steve Ribke or I, and eventually Dave Riffle went in and we took all of this data so that we could track the progress and really show and prove the energy savings and what we were telling them. And that initial pilot project showed a savings of nearly 280,000 gallons of water, which thankfully led to, in 2015, a retrofit of the entire building. And that caused a 49% reduction in chilled water pumping and an average savings of $23,000 in chilled water savings. During that process, somewhere there between 13 and 2015, the district chilled water plant sent a technician over to check all the equipment and to check the meter in the basement because they were certain that something was wrong with the equipment because the chilled water usage had dropped so drastically. And we were really thankful that there was no problem and that it was due to this massive drop in chilled water pumping. And we, as you see on the chart there, we took their average maximum July flows from 550 GPM down to 350 GPM, and that's an ongoing savings today in 2020 for that building. And that whole project, the retrofit, led to a simple payback period of 2.4 years.
So after the success of Citizens Plaza, Chad and some other people involved invited us to look at the next building for them, which was the Andrew Jackson, about a block and a half down the street from Citizens Plaza in Nashville. A little bit larger building, but again, another one, they were experiencing these same thermal inefficiency surcharges, still purchasing this water from the district chilled water plant, going through a lot of the same scenarios. As Kevin just mentioned, pretty neat. In the bottom of this one, it's actually in the parking garage downstairs, there is a large meter and we could see the flows and the delta T of the building. So throughout this project, we were able to even get a real check-in from the building of what was going on. We were able to also constantly download data. So this is one example of data we downloaded from one particular unit in 2018. This is looking at essentially July through September of 2018 of one particular valve. And it's very interesting what we can do with these valves. We get an eye into the system and an eye into the point of heat exchange or energy consumption. We can really see what's going on with a particular unit. We can look at flows, we can look at the modes the valves are in, we can see what the valve was being commanded to do, as well as what the logic took over and actually did. So again, this one's May 31st through September 30th, roughly 2018, 122-ish days. We can also look at the delta T. So we can see here in this graph, we had the delta T manager set right in the middle of June. It basically got set for 14.5, and we can see what our actual delta T started to do. So again, this is 6 months, 5 months of data kind of compressed into this image, but we can see what's really going on with our units and very much look at all this data. This particular unit, we can see 42% of the time the logic kicked in. That's what my little graph on the bottom is showing. And what we're saying by that is 42% of the time the valve wanted to overflow. The system was trying to push too much water through. I would have inefficiently used that water, essentially just passed it through the coil, not taken a heat exchange or heat transfer out of that water, and been very inefficient. For this particular valve, that accounted for roughly 3.5 million gallons of water over that time period that would have just been wasted. So eliminating that waste is eliminating over pumping for the system and eliminating overflows and those thermal inefficiency surcharges. One thing to mention here too is the pump affinity law, which we ran into a bunch for them. Pump affinity law just states that a change in flow can be a cubed effect on our pump. Moreover, if we know our delta T was 14, like it's designed for this example, and they were achieving 7 or half of 14. That's twice the flow and 8 times the pump horsepower. So a dramatic effect, and that really shows why this was such a big deal to them and those costs were so huge. Andrew Jackson turned out to be 32 energy valves, 30 air handlers, again, 1 per floor, and 2 makeup air units. The simple payback period for this one was estimated at 1.2 years, eliminating those pump inefficiencies and those monthly surcharges they saw. This project has also continued. Now we've looked at one other building has actually been completed, and we're doing a lot of the data analytics of that building now. And there's another building we're now looking and sizing the energy valve for all the particular air handlers that are on this one as well. So this is still an ongoing project. We're moving forward with the state of Tennessee, JLL, and still achieving great results that we can keep showing and benchmarking for them.
Excellent. Thank you so much, Dave and Kevin. Before we move on to questions, please remember to follow Belimo on social media to keep informed about what's happening. At this time, our presenters would like to answer your questions. Please type your questions into the question box and our presenters will answer as many as possible. If you think of any questions after the webinar or we are not able to get to your questions, please send us an email at training@us.belimo.com. And I do see a couple questions coming in. The first question, what programming does this device require?
Yeah, thank you, Ron. So to be actually honest, there's not a lot of programming. The logic lives inside of the actuator. So when you order this product, you order it for the sized flow rate of the unit, meaning if I have an air handler that's designed at 100 gallons per minute and a 12-degree delta T, I order it for those numbers, and that's all. I command and control it the same way I would have in the past with everything else. These buildings had no changes to their DDC building automation systems. They just had changes to the units with these valves.
Thank you. Question 2, does this valve communicate with the building automation system?
Correct. Yes, it does. So we can communicate the same way as valves in the past. These are actually smart valves as well. So they have the ability for a full backnet integration or even a cloud integration if a customer was interested. So many different levels of communication from what we've always done in the past to the smart cloud optimization we can do in the present and future.
Okay. What are the installation requirements for this?
Yep, so installation requirements are pretty simple as well. We are using a wet flow meter with this, so we do require 5 valve sizes coming into it, essentially eliminating that turbulent flow that comes in my flow meter. I require nothing leaving the valve, so there can be an elbow coming off or a 90. It can be on the vertical if they need to be as well, but again, 5 valve sizes coming in. So if I'm ordering a 1-inch valve, I would have 5 inches of straight pipe in front of it with nothing inhibiting flow at all.
Okay. Can we get BTU out of this device?
Yes, that's a good one. We hear this one a lot. So since we do have flow meters and temperature sensors embedded with this valve, it is not only a control valve, it is also a flow meter. It is also a full BTU meter. So we can get that information that's stored locally on the actuator. Via BACnet, we can pull that information out. Via feedback, we can also pull that information out, but we can use this as a control valve, a flow meter, and also a BTU meter now.
Okay, thank you. Were the original valves 2-way or were they 3-way?
Those original valves were 2-way globe valves.
Okay. Let's see what we have coming in. Is it also possible to get white papers on executed projects with the energy valve?
We have a bunch of success stories, case studies that are on our website. You can see there are some white papers available, correct? So we have a good amount of different case studies, examples, white papers on our website, or your local person can also put you in touch with those. So correct, there are materials available, yes.
Okay. Does the time to cool a space suffer by limiting the flow?
What we do is we maximize the heat exchange or that heat transfer. So if we can think about if a coil is designed for a certain heat transfer or delta T for all sake of words, we know that by overflow, we lose that delta T. We are inefficiently using that water. All we're doing is we're making sure we're using that water as it's designed. We're eliminating the overflow, which means we do not affect the discharge air temperature or by time, I guess, if that makes sense. We just maximize the efficiency of the heat exchange and that heat transfer and do it as it was designed.
Thank you. How does this work if we are trying to maintain discharge air temperature?
Yep, similar to our last question. So in a normal system, a normal scenario, you'd have some sort of building automation system, BMS. That system is by some PID loop or some algorithm is affecting and controlling discharge air. Once they do that, they send a control signal to the valve. In the past, that valve would have gone to a position. That control signal will correlated to go to 50% open or go wherever. Now we know more than that. So now we can go to a flow instead of a position. So as pressures change and that flow moves, we can be pressure independent and get to a certain flow. And as that delta T changes, we can go and maximize that delta T. So no change overall to what we're doing. Again, we're just maximizing the efficiency of how we do it.
Okay. What are the largest and smallest energy valve sizes available?
It's available 1 gallon a minute, all up to 713 gallons per minute. In size range, 1/2-inch valves all the way up to 6-inch valves.
We have time for one more question. Does the speed of response need to be commissioned?
No. So in commissioning, they're just going to be doing a flow verification. They're going to verify this unit was supposed to see X flow. We're going to make sure we can achieve X flow, set the valve to the design parameters of the unit. That's pretty simple and straightforward. Now we get that feedback from the unit of not only position, but now flow and delta T. So commissioning just involves verifying whatever the design flow is achievable.
Excellent, thank you. We'll take one last question here. How does water quality affect the performance of the energy valve?
Yep, that's a good one. So what we use in an ultrasonic wet flow meter today, which is a very robust, resilient flow meter. And on top of that, we use our characterized control ball valve, the one we've been using, again, since 1999 and works very well in a wide array of water quality, we should say. So overall, we've had almost no issues with the quality of water within a normal HVAC spectrum, I should say. So as long as everything else is operable in the system, these valves do not have an issue. Still get you your good accuracy and tolerances from the valve. No concerns there.
Excellent. Thank you so much, guys. Once again, thank you so much for attending today's webinar. I'd also like to thank our presenters, David and Kevin. If we had not gotten answers to your questions, we will get them to you via email. And if you would like a copy of the webinar and or think of questions after today's webinar, please email again training@us.belimo.com. Also, please join us for our next webinar, which will be held on April 1st at 1 o'clock Eastern Time. And the topic will be Belimo's room sensor launch. Thank you all and have a great day.